Finished our discussion on forces and Newton's laws, and now we're actually going to get into a new topic, and that is work. Um, we'll also talk about energy in the next upcoming lessons, as well as power. So, in your books, I think that's the whole entire unit is titled Work, Energy, and Power. I think in the past lessons, we've already touched a little bit on energy, so it's not going to be a completely new discussion for you. So, our learning objectives for this lesson is that at least you should be able to define what work is and perform various calculations involving the equation of work. So, let us just get straight into it. So, how do we define work? So, work is, in simple terms, defined as the transfer of energy. So, for example, imagine you were stuck on road, maybe your car stopped working, and this is you. You're gonna push this car over a certain distance. So, we call this xi, initial distance. Maybe you want to get it to this point over here, which we call xf. So, what you're going to do, you're going to be transferring your energy to the car to move it over this certain distance. And we say if you have done that, you have done work on the car, and your work will actually be positive. But the opposite can happen. Imagine now you're trying to push a car up a slope. Okay, this is you trying to actually push this car up, but in turn it actually pushes you away. So we're actually you trying to move it up, and then so that means that the car is doing work on you because it's transferring its energy on you, and now instead of going forward you now moving backward with the car. So that is basically how we define work. And then work done on an object is on an object by a force. So work is done by a force. When you push in that car, you are exerting a certain force on it, and work is given by the product of that force that you applying perhaps on a car over the displacement. So remember I said you there you are in your Vrpa, you're trying to move this car from here maybe to this point xf. So this is where you're trying to get your car to move to. So we have that change in x, which is our displacement. So change in x will be given by xf, the final position, minus the initial position, and then the cos of theta. So this is the equation for work. And then so let me reiterate again. So work done on an object by a force. So remember, you are pushing this car, you're doing work on the object, you're applying a certain force in this direction, your displacement is also in this direction. Is the product of the force that you're applying multiplied by the displacement and the component of the force that is parallel to the displacement. So that's why we have that cos theta over there. So now work is measured in joules J. You know force is measured in newtons, displacement must be measured in meters, and theta here is the angle between F and X, and you know it's measured in degrees. Now remember that work so we've spoken about vector quantities, we've spoken about forces, um uh, what is it? What else did you do? Velocity, acceleration, and many others. But now work is actually a scalar quantity. So you don't need to provide the direction. So you don't need to provide negative F or positive whatever, because this theta here will actually take care of the direction for us, and then you will see what is it that I mean. So there are also two things that are important in terms of work, and the first thing is that which this force that is acting on the object, and then as well as the displacement of the object. So this displacement can happen either horizontally, maybe it's moving left or right, or it can actually happen or up or down. So for example, maybe you're trying to move this block, like I've mentioned, to this point over here. This is xf, this is xi, and then you have a change in x. So that's your displacement, and your force is also in that direction. Or maybe you're trying to move it up somewhere. So you're trying to move it, so this is your yf, and then maybe you're trying to move it from yi, so this is your initial position. So here you would actually have a change in y, over there, and then your force is also going to be facing up, which is your force going up. So it can either be a change in y or a change in x. So when a net resultant force is applied on an object, the resultant force accelerates the block across a distance x, and then we say work has been done to increase the kinetic energy. So when a force acts on an object and it moves it across a certain displacement, we say that work has been done. So this will be maybe in the x direction when you're moving that block from one point to the next. But now, let us imagine a different situation when we are moving it up or down. So now, if that net resultant force is applied and it's you actually lifting the whatever, maybe a block over a certain distance, we will have potential energy of your block will increase. In this case, you change in x because your velocity will be changing, your kinetic energy will increase. So now remember, for work to be done, there has to be a displacement. So if you are here and you're pushing your car, this is you trying to push this car forward and it's not moving, then we say no work has been done. No work done. So for work to be done, there actually has to be a displacement. Another scenario where there's no work done is if maybe you are moving in this direction, but then your applied force is in the vertical direction. So you'll see that the angle between these two, maybe this is your change in x, is 90 degrees, and the cos of 90 will actually give us 0. So no work is done here. So at least that thing, that the force that is acting has to at least be parallel to your displacement for work to be done. If it's perpendicular, no work is going to be done. And now we're going to talk about positive work and negative work. So let us consider a situation whereby you're trying to move this block over a certain distance, and then you are applying a force there. Let's say that force is like 25 newtons, and then you're gonna be moving it to this position over here, and maybe a change in x from here to here is given by 10, and then the angle between between the change in x, let's say, is for theta here is like 45 degrees. So how do you then find the work done by this force? We would simply say the work done is F change in x cos of theta, and then you have all the values that you need. It's just a matter of putting it in your calculator. It's the same thing. So we have 25 multiplied by 10 multiplied by the cos of 45, and you're going to get, I think, about a value of 177, which is positive. And then we will actually say that work has been gained by the system, so it's joules. So work, so 177 joules gained. If now the angle changes here in our schematic, it's still moving in this direction, but now your force applied is here. Its value is still 25 newton, and now this is the angle theta from here, and let's say theta in this case is like maybe 120. So we still do the same thing. We find that work is going to be 25 the cos of 120 multiplied by a change in x, we said it's 10, and I think you're supposed to find a value of about negative 125 joules. So when work is negative, it means energy has been removed from the system, so 125 joules are lost. So that's the difference. If it's positive, it means work has been transferred to the system. If it's negative, work has been taken away from the system. But then we can also have a situation, a typical situation whereby work, the force is also in this direction, and as the displacement is also in this direction. So there's no angle. So the angle between those is 0 degrees. We said x was 10 meters, and then the force there was given by 25 newtons. And to calculate work, we will simply say F change in x cos of theta. So we have our F is 25 multiplied by 10 cos of theta of 0, and this thing I think is going to give us about 250 joules, and we will say 250 joules of energy has been gained because that value is positive. So that is just simply how we do some very basic calculations involving work. But then we can also talk about net work. So remember, we have net force. We can also talk about net work, which is given by F net, a change in x cos of theta. So let us do a calculation to calculate the net work of a certain object. So here we have a question, and it reads as follows. Calculate the net work done on a trolley where a force of 30 newtons is applied. So FA is 30 newtons, and then the trolley moves 3 meters. So the displacement is 3 meters to the left. The force of friction is 5 newton to the left as well. Okay, so how do we go about answering this question? Well, the first thing I would suggest is draw a free body diagram of that situation. So here's a trolley, and then we have FG, and then we have FN. So, and then we also have a force applied, maybe it will be in this direction. So the trolley is actually moving to the left. So no, I'm lying, it's being pulled to the left. So meaning that friction couldn't have been to the left, actually it was to the right. So we have the F applied, and then we have friction in that direction. So you have, so remember, we are only interested in the vertical motion, so we can ignore Fn and Fg for now. So if you want to write F net in the horizontal direction, we would say we have Fa applied, and then Fa applied, and then let's say maybe left is positive, and then right is negative. And then we have ourselves 30 so this Fa plus a negative of friction there. So we have 30 minus 5, which gives us 25 newtons. And then we have F net, we have the change in x, we can calculate the net work done. W net is equals to F net change in x cos of theta. Then we find that to be 25. It was displaced over 3, and then the displacement as well as the direction of motion is actually in the same direction. So the angle between F net and a change in x is a cos of 0, and you find that value to be let me see, I think you're gonna find it 25 times 3 75 joules, which is positive, so meaning 75 joules gained. So there are also many other ways in which you can do this question. So you can either say, I'll calculate the work done by individual forces, and then only then add them to find W net. Or I'll first find F net and then substitute it here. So for example, if you were to add all the forces that are doing work, so we would say W net equals to work done by the normal force plus work done by gravity, work done by applied force, work done by friction. And then here you'd have Fn change in x cos of theta plus Fg change in x cos of theta plus Fa change in x cos theta plus Fr change in x cos theta. And then you would just add everything together. So you have 3, you have the angle theta, which is 0. And then so theta so you have to realize that theta for the normal force, the angle between this applied force and the normal force would be 90, so theta would be 90. And then for gravity it will also be 90, it's perpendicular. And then for applied force it will be 0. For this one, theta will be 180, and you actually gonna come to the same answer as 25 joules. And yeah, I think this brings us to the end of this lesson. We will still continue to talk about work in the upcoming lessons.